Hey guys, thanks for tuning in. Garen here, Power CNC. What follows is a session of fusion of where I explain how I'm going to thread this part. And I've already threaded this, so welcome to the future. I successfully rebored and threaded these two holes. I had to plug weld them, rebore them, and then rethread them because of a tooling mismatch. Program for one tool had a different tool in the spindle, ended up messing up the threads. So let me try and preface this with a little bit of humility. I'm just getting into single point threading. If you have any comments or suggestions, anything positive by the way of feedback, please leave it in the comments below. And hopefully this little Autodesk fusion session makes sense and is helpful in some small way. So in total, I bought 3 tools from Mari Tool to do my single point threading. First tool I bought is the 0.180 diameter by 0.5 max depth single form thread mill. This mill should thread 1/4 inch thread, 20 to 56 threads per inch. And it is 0.180, that's smaller than 6 millimeters, smaller than 5 millimeters. So I should be able to get into a 6 millimeter hole and tap that out as well. The second tool I bought is a 0.24 diameter by 0.625 max depth single form thread mill. And this will do 5/16 thread, 18 to 48 threads per inch. And then the last one I bought, it's the biggest of the 3, it's 0.290 diameter by 0.875 depth single form thread mill, and this one is rated for the 3/8 16 thread, and I tapped a lot of 3/8 16. So this will do anywhere from 14 to 40 threads, and I've already confirmed that this will also machine my 10 millimeter holes that I do a lot of. All right, gents, this is what we're working with today. If anyone's curious, when I run these simulations, I'm actually running this in Chrome in a browser. I've used a lot of screen recording software, but I can't seem to get any of the software to bring up these other menus. So yeah, that's where I am. Let's do a general overview of what I've got. I plug welded the threads, okay, and then partially welded in these bores. I didn't need to, but I did. I'm a terrible welder. You'll see that. I weld like I tie knots. I've got this divided into a couple of different boring operations. I'm using a 1/4 inch end mill. I'm going to bore out this counter bore here. And actually this counter bore, I need to redesign this. This counter bore is a remnant of the past. I wanted to get my threads to a certain depth, but I didn't want to thread that deep, so I opened it up with a counter bore, and then I put in my threads in this 8.5 millimeter hole. But now with the thread mill, I don't have to do that. So this will be the last block that looks like this, unless I'm using an actual retention knob, which requires a counter bore, and then I'll still do that. So I've got that bore there. And then I'm going to bore out the 8.5 millimeter hole. It's 15 millimeters deep from this point all the way down to here, 14.9. I'm not going to go all the way down. I'm only going to thread 12 millimeters down. So I'll go down with the bit, and then I'll have 3 millimeters of clearance at the bottom to give my thread mill room. I'm going to do this. I don't have through spindle coolant, and when my 1/4 inch end mill is in the hole, who knows how much coolant it is or isn't getting. So I've split this up. I'm going to do the first 10 in this op, the first 10 millimeters. I'll retract, and then I'll go down for the last 5. Does it make a difference? I don't know. I don't think so. Maybe it does. Probably would in aluminum, but we're rolling with it. See if we can extend tool life that way. I'm going to run the chamfer again. I already have a chamfer on the part, but I'm running it again because I got a little weld spatter on this ring, and I'm going to clean that up. And then the fun part, the threading. This is the tool I'm using. It's the 0.29-inch thread mill. Well, this is the hard part for me. I know it has 4 flutes or 4 cutting parts that cut, right? With one single cutting edge. All right? Diameter is easy, 0.29. The shaft diameter is bigger. That's about 3/8 of an inch. And then length below holder, that was easy enough to put in there. And then the flute length, this is where I just didn't know. It's like, do I get in there with calipers and measure that? Do I use a formula to figure that out? But what I did do was, I took their, so the flute length here has to basically equal in fusion the maximum thread pitch that I can cut. So I took the maximum thread pitch, did the math, and then put a 0.0714 flute length, and then the minimum 0.025. That's how I knew I could do that because Meritool called it out, and then I put that as the flute length, and it seems to be working. And then for the tool pathing, this is what I came up with. I am tapping this in S7. It's annealed. I've got an RPM, a spindle speed of 2370, which is about a 55 meters per minute surface speed. I've got a cutting feed rate of 289 millimeters a minute with a feed per tooth of 0.03 millimeters. And in inches, that is 180 feet per minute surface speed with a cutting feed rate of almost 11.5, and then a feed per tooth of 0.0012 inches. Okay? And then, does it say it on here? Yeah. So I'm stepping over a maximum of 0.012 inches. And I figured that out because I just wanted to start with 3 equal passes. Okay? So 1, 2, 3, and then a finishing pass, and it'll be good. And it should be done. So that's my logic. So in passes, I am running this with wear so that I can use a go-no-go gauge to make sure the threads work. And if it's too tight or it doesn't fit, I can increase the wear. Like I said before, I've got 3 stepovers. There you go. The 0.012 inches, I believe I said, that equates to 0.305 millimeters. Okay, and then I am doing a multiple passes, so 3 at 0.305. The other tab that is important is the geometry tab, and this is where I put the thread pitch. Okay, so this is M10 1.5, so that's pretty easy. That's it's just straight in 1.5 millimeter. It's a little more complicated when it's 3/8/16 because I have to find the thread pitch, which is 1/n, right? So 1/16, and that goes there. And then there's the pitch diameter offset. And so that's basically, well, I hope this menu comes up. The first picture is offset equals 0 millimeters. That's when the tool just barely touches the face, or it's the diameter of the hole that you've bored. So for the 10-1.5, that is 8.5 millimeters. And then the offset is between 8.5, and then how deep those threads need to go in after those 3 passes. All right, so what is that distance from the 8.5 to the distance to the peak where it stops cutting? And in here, that pitch diameter is 1.624. I keep a spreadsheet, and then for this math that I figure out, and I know I'm going to need down the road, I put it in here in my little calculators tab. So these are notes that I keep, and I keep this on Google Sheets so I can find it on my phone, or I can find it on the laptop, which I'm on now. So for example, this is my tool library. This is how I want to organize my tools. okay, all the way from facing to the end mills. And this is just organized on how I use these. So I've got flat end mills, ball end mills. I've got my chamfer, my V-bits, 9s for spots, 10s for drills, 11s for any tap, and then 12s are for my probe or for my master tool. That's kind of how if anyone wants me to go over that in more detail later on, I can. But I also have a calculators thing, because I'm always calculators tab. I'm always dealing with inches and millimeter, and I'm at my age, I'm not great with the math. So for example, let's say I want to do a chamfer at 0.25 millimeters. Well, that's about 10,000ths of an inch right there. And now let's go back to the pitch diameter offset. If I've got a 3/8 tap, then I boiled down that math. Have you seen that math equation with all of the fractions and stuff in the machinist handbook? Well, I boiled that down to this, 1.0825 times pitch, and that equals your pitch diameter offset. So for a 16 tap, or 3/8 16, that's 1 divided by 16, right? And then times the 1.0825 gives you your pitch diameter offset. In inches here, remember, in Fusion, I'm running in millimeters, so that might look different from what you just saw. So for metric, it's easy, because they put it right there, 1.5. So I just times that by it, and I know I need to go over 1.624 millimeters in order to make a complete thread, plus any wear that I might need to do based on material and tool wear. Does that make sense? Let's see if it works. All right, guys, that's all I got on single point threading. Please let me know what you think of the strategy, particularly the 3 stepovers. Seems to be working pretty good, and it's a lot prettier thread. So, as always, thanks for tuning in. Catch you on the next one. Bye.